For exercise 3, we have a lot of options of how to group all of these ones together. We could do, maybe the most naive things would be to just individually group each of these squares into their own group. But of course, that's not going to be very efficient. Each one of those is an extra term, and typically doing something like that is never going to be the minimal way to group these together. So if we start thinking of other options, we could do something like this. We could group these two together and then maybe make two vertical groups out of these. That would be a possibility. But again, the goal is generally to try to have the fewest number of groups and also have each group be as large as it can possibly be. So let's say maybe our first choice would be to notice that these 4 ones here are all in a line. We can make a group of 4. We can make a group of any power of 2. So it could be 2, 4, or 8. And this will work. So that's a nice group of those 4 there. And then we might see, well, I can make a group out of these 2 and then a group out of these 2. And that's better than the previous option. We still have 3 groups, but because this group is larger, it will eliminate some redundancy because we can eliminate the variables that are on top. Actually, this group of 4 would eliminate both x1 and x2. We'll get into that later. But we can do better than this because rather than having these 2 groups of 2, we could turn this into one group of 4. And to do that, we have to remember that this Carnot map is sort of wraps around on itself. We can always wrap around. In this case of these 2x4 maps, generally we only ever think about wrapping around left to right, but we could technically wrap around the top and bottom also. But that means that these 2 squares on the far right are considered to be adjacent to these 2 squares on the far left. So we can just sort of rotate around this and wrap back to the other side. And if we look at it that way, then we can see that if these 2 and these 2 are adjacent to each other, then we just have a square of 4 ones to capture there. So I'm going to have to draw this as best I can, but we're going to do something like this. We're going to grab these 2 ones, and then we're also going to grab these 2 ones, and we're just going to write this the best we can, but basically this is meant to represent that this group here starts but then continues over to the right, which wraps around to the other side and captures these 2 ones. So now we have this square of 4 ones that are spanning the 2 edges of this map, and then we have this long row of 4 ones there. So now we only have 2 groups. And each of those groups is as big as we could conceivably get it. There's no way to have a group larger than 4 in this diagram. So this would be, this would make sense to be our optimal, our minimum Carnot map, or minimum grouping. Because, again, we have 2 groups, and there's no way to capture all of this with one single group, with all ones in it at least. And each of those 2 groups is as big as we could possibly make it because we can't have any group that has 8 ones in it, and so 4 is the largest size that we could get to. So now we want to write the expression that represents these groups that we chose. And let's start with the long row here, the horizontal group. Like I said before, this group of 4 ones here is going to eliminate both x1 and x2. And the reason is, if we go between these different squares, we see that some of them have x1 and some of them have x1 prime, or not x1, which means that regardless of what x1 is, we would want the function to output 1. So yeah, in that sense, it doesn't matter what x1 is. And I guess in a more practical sense, what that really means is if we're designing a circuit, we don't actually have to check the state of x1, because regardless of if it's a 1 or if it's a 0, the condition is still satisfied. So we don't have to include that in our circuit at all. So that's what's happening here. x1 is being eliminated because we don't need to check its state, because no matter what state it's in, it's still acceptable. And the exact same for x2, because we have x2 and we also have inverted x2, or not x2 in here. So we can ignore both of those variables. And the only variable we have to consider is x3, because all 4 of these squares correspond to x3, and none of them correspond to not x3. So x3 is required, so that's going to be our first term. And then next we have this group of 4 in a square that wraps around, that spans the edges of the map. And here we have to look at what's going to be eliminated. We could see first that x3 is going to be eliminated because we have 1s on the top and bottom rows, which means we include both x1 and both x3 and not x3, which will eliminate those 2 variables, or that 1 variable. And we want to look to see if anything else is changing. So the 2 columns that are included in this group are the far left column and the far right column. And in the far left column we have x1, and in the far right column we have not x1, which means that those would be eliminated because both are included. Either state is going to satisfy our condition, should produce an output of 1. So x1 can be eliminated. But then x2 is x2 on both sides of this group, or that is the not x2 or the inverted x2 is only in the middle, and that's not being captured in this group. So x2 is required because x2 has to be a 1 if we're thinking about this as this would be satisfied if x2 was a 1, and that happens no matter where we are in the group. So we need x2, but we do not need x1 because it changes left to right from its regular form to its inverted form, and the same for x3, moving top to bottom in this group. We switch between those 2 forms, and so x3 can be eliminated. So finally we have the long horizontal group on the top, gives us only x3, that's the only condition we have to check for that. And the group that spans this square on the edges is x2, that's the only thing that didn't get eliminated there. So x3 plus x2 is the minimal sum of products form for this map. And it is very minimal. We can't possibly get rid of either of those things based on the information we have there. So this is the simplest circuit that we can make under those conditions.